Hey guys, this is Michael with Breaking Concepts here today. Thank you so much for watching this video. Today we're going to talk about sequence, and this is the first video within our recursive sequence and this application series. And so, yeah, it's important to go back to the basics and kind of understand what sequences are. Just a quick recap, right? This is going to be a quick video. So let's start off by, imagining the sequence 2, 3, 4, 5. And in sequence, the way we represent the term is we're going to call A1 equals to 2. And just for a quick recap, A1 basically stands for value, right? And 1 within A1 here stands for the position. Position as in, what is the address, what is the position of the term within the sequence. You have 1, 2, 3, 4. So obviously A1 is the first position, the first term, and it's equals to 2, as you guys can see here. And if you guys are looking for the second term, we will write A2 is equals to 3, right? And if we're looking for the third, the fourth, same thing, we're just going to use AN. So kind of just give you guys the review here. If we were to find the nth term, right, we're just going to write the AN is equals to the value of the nth term within the sequence. And sometimes, like you can see from here, 2, 3, 4, 5, this is basically just plus 1, plus 1, plus 1. We're starting to see a pattern within our sequence. And in that case, we actually define AN as not only just a value, but also as a function of n. Now, what I mean by that is, remember a function is that we input something, right? And we'll get a value, right? This is what a function is. So here in AN, what I mean by AN as a function of n would look something like this, right? You want to input n, perhaps is the position, maybe 1, 2, 3, 4, 5, and throughout that function, it will give you an output of a value, which basically is this. And we're going to take a look at one example that is exactly built on this. So here we have the function AN equals to n over n plus 1, and the question says find the first five terms and starting from A1. And the reason, by the way, we have starting from A1 is because sometimes we have starting from A0. And what that means is very simple. It just means that start from the 0th term. If you do programming like Python, whatever, you would know that sometimes programs, we normally start from 0, 1, 2, 3, whatever. So just be mindful that there's the reason why we say starting at A1 or A0, we have to be very aware about that. So going back to this question, we can first find the first term by substituting n equals to 1, right? So A1 is going to be equals to 1 over 1 plus 1, which is basically equals to 1 over 2. So if we do this for 2, 3, 4, 5, we're going to get the answer for this. And as you can see, we have the second term, which is equal to 2 over 3, until the fifth term, which we get 5 over 6. So let's move on to another example. In this example, interestingly, we have AN equals to -1 to the power of n minus 1. So let's just say we find the first 5 terms for AN here. So if we start from A1, as mentioned, let's sub n equals to 1. We're going to get -1 to the power of 1 minus 1. And 1 minus 1 is basically 0. So we have any integers, any math or whatever, to the power of 0, even for e, you get the answer of just 1. And let's do A2 together. You have -1 to this time it's 2 minus 1, and 2 minus 1 is just 1, right? So -1 to the power of 1 is just -1. Okay, and then we can try A3, you kind of get where I'm going. A3 equals to -1, 3 minus 1, 3 minus 1 is 2, so -1 to the power of 2 is basically 1, right? Because it's -2, all the negative values become positive. It's an even function. Okay, so let me do A4 and A5. And so as you can see from the results here, A1 to A5, we can see that the values are just fluctuating between 1 and -1. And from these two examples, I just want to stress the importance that to realize sequences are discrete. Discrete. And what I mean by discrete is if you take a look at we call the input of the function, the ends, is 1, 2, 3, 4, 5. You see that these are not 1.5, they are not like, square root of 2, whatever. They are positive integers. And this means that the input, or we will say domain of our inputs, which means, right, the range, like the domain of our input is equals to positive numbers. Now, the idea of discrete is super important because as we move forward, we can see more clearly from the graph that if we were to plot a graph, let's say like that, a discrete function would give something like this. Even though, let's say y equals to x goes like this, they are kind of have the same trajectory, but because this is discrete from 1, 2, 3, 4, and so on and so forth, it is not the same. And it is very important to realize this because this is the basis of recursive functions. So here we have a sequence. So pause this video and try to find the general formula, which is an equals to something. What is the function of an? So assuming you had a chance to try it yourself, to solve this is actually very simple. I'm going to use 3 colors for 3 parts because of solving this sequence. So number 1, we're going to first of all look at the numerator. The numerator, we can see that everything is just plus 1. Plus 1, plus 1, plus 1, plus 1, plus 1, right? Plus 1s. So on and so forth. And so the way that I'm going to structure this is n plus 1. Because it's plus 1 plus 1. But obviously, this doesn't really work. Why? Because if you sub the first term a1 here, right, n equals to 1, you have 1 plus 1 is basically 2, right? That doesn't make sense. And so instead, we have to sub n plus 2, where we're going to get 4, 5, 6, 7 by substitution. Okay, so we have the answer for numerator. And now let's find the one for denominator. For the denominator, we will use actually, with denominator, we can see that it's just 5 squared, 5 cubed, so it's just the power of 5, right? So the denominator will do 5n. And last but not least, don't forget the signs that you see here, just plus, minus. And how do we do this? It's actually pretty simple. We have done it just now. So signs. To do a fluctuation between positive 1 and negative 1, all we got to do is we have a negative 1, and then we take it to the power of n minus 1. Simple as that. We've just proved it in our previous example. So combining all these, right, we will get negative 1 to the power of n minus 1 for the signs, and n plus 2, 5 to the power of n. And we're done.